We need a few results about parallel lines now that we actually have the parallel postulate. And the first one, and one of the key results in this section, we'll talk about the median, so I define it here. The median is a line drawn through the midpoint of one side through the vertex opposite it, and you see the red dotted lines are the median segments for a triangle. But the thing that, well, let me pause and make a whole sentence. So the transversal congruence lemma is really important, but it's a toolbox theorem. It's one that we use to prove something, and then we kind of never see it again. But it is a really interesting theorem, and it's a basic theorem, easily proven. Let me talk about why we're using it. It goes here because it's an easy basic theorem that we can prove right away. But if you look at the beginning of the triangle section in 3.6, you'll see that there are different types of concurrences, right? The medians are concurrent. If you take the perpendicular bisectors of all three sides of a triangle, they're concurrent. If you take the altitudes of a triangle, they're concurrent. The angle bisectors are concurrent. And what's cool is that we can use the point where they are concurrent to make certain things. Like, for example, the center of the inscribed circle is at the concurrency point of the angle bisectors. So if I want to draw a triangle, I am not going to get this right at all, but an inscribed circle, sorry, is one that is tangent to all three sides, and the circumscribed circle is one that's tangent to all three vertices, and that's a horrible drawing, but you get the idea. The point is that if I want to find the center of those circles, I find the concurrency point, and they have definitions. And I only throw that out because we'd like to do this for all of these, but it turns out that the median concurrence is actually a very primitive idea, and we can get it as soon as we come up with this toolbox theorem. This is what we're going to use the transversal congruence lemma for. Actually, we're going to use the theorem. So let's talk about this. So the idea for the lemma is that there are three parallel lines and it's cut by a transversal t. So t is the original line. And if the transversal cuts these lines in such a way so that congruent segments are made between the parallels, right? So CB is congruent to AB, right? We have this congruence going on. When that's true, then every other possible transversal that I could draw that cuts those same three parallel lines will also have congruent segments between the parallels. Okay, so that's the idea of the theorem, and it's not the one we need to prove the median concurrence theorem. The one we actually need is the transversal congruence theorem, which says that for any amount n parallel lines, and it turns out for the median concurrence we'll actually need 5 parallel lines, but any number of parallel lines that when they're cut by a transversal, the line segments between the parallel lines are congruent. If that's true for one transversal, then it'll be true for any transversal that I can draw. This is the full transversal congruence theorem. And if you think about it, it requires an induction proof of the lemma, using the lemma. So the lemma actually turns out to be the motor, right, that will push, it's the base case from which we'll be able to push the transversal congruence theorem through using an induction proof. Okay. And once we have it, it turns out that the median concurrence theorem is pretty easy to prove. Why? Well, you'll have to, I'll prove this theorem and you'll just have to watch it. I don't see a real easy explanation. The theorem's a little bit technical, but it totally relies on theorem 1. So the proof of theorem 2 totally relies on the proof of on the result from theorem 1. And then we just have a couple more parallel line theorems. 2 lines parallel to another line or parallel to each other. If one line intersects one of 2 parallel lines, then it intersects the other. And then I want to talk about this one specifically because some people come from K-12 schools with the idea that this is the definition of parallel lines. It's true. It's a theorem we can prove in Euclidean geometry that parallel lines are everywhere equidistant. But unfortunately, some people, when teachers are, I guess, are giving the idea of what it means to be parallel, some students think that that's the definition of parallel. The definition of parallel is very simple: two lines that don't intersect. And it's only in Euclidean geometry that parallel lines turn out to be everywhere equidistant. So that's all there is. This is a nice section, just a few theorems about parallelism, and one really important result, toolbox result, that is going to allow us to prove the median concurrence theorem.